Yes, we can.
Perfect. Okay, let's go. So as Lorenzo said, I'm going to give you an overview of the data flow used in Run3 and try to highlight the main parts on how it's different from what was done in Run1 and Run2. Okay, perfect. So this is an overview of the run flow in Run3, data flow in Run3, sorry. So starting from the detector and reading out all the information, sending all the information to those different servers. Here's this group of blocks is what we call online processing. So this is all under the responsibility of the RTA group, so real-time analysis group. And the last part here, which is more linked to offline processing, is the responsibility of the DPA group, so the data processing and analysis. And I will try to go step by step on how the data is taken care of and what each step actually means to the best of my capability. So what changed between Run 3 and Run 1 and Run 2? So as you can see here, we find the same block. So we have the detector block, we send the data up to an online block, and finally an offline block. So more the structure and the overall scheme is the same. But if you look in more details, we skip a step between data from the detector to our offline processing. As you can see here in Run 1 and Run 2, we've already heard before that we had a hardware trigger that we don't find in Run 3, as Prima already mentioned before. So why is that? Why did we want to remove the hardware trigger? So first, a quick word on triggers. So we have a lot of information coming from our detectors. We have a lot of sub-detectors. All of them can produce a huge amount of data, and we're limited by what we can actually store. So all the we can't process all the data onto storage to be analyzed offline. So we need to efficiently select what kind of information is going to be useful for us, and so that we can actually store this to disk to be analyzed later on. And also, as she mentioned, in today's run, if you look at the prediction rate in the Run3 conditions of BB bars and CC bars, you can see that we are at the megahertz level, which is the bunch crossing rate in LHC. So in all the events we're going to have at bunch crossing, we expect to have, in most of the events we are going to have at bunch crossing, we expect to have also useful and signal information or signal candidates. So to try and select what we actually want to store before, we implement triggers. So there's two types of triggers, hardware and software. So the hardware triggers are generally based at the sub-detector level. So we're going to use a hardware, so generally FPGAs, to do a cut on the information that is produced from one of the sub-detectors. So typically this was done for run 1 and run 2 on information from the calorimeters. Where in software triggers, we need the data to already be accessible in computing forms to be reprocessed on softwares, as the name says. So one of the things that I find interesting here is that the hardware, you only have information from one sub-detector, whereas in software triggers, you can potentially use information from different sub-detectors, which is interesting in our case, because what we want to select for the signatures of events we want to select, we need more complex quantities. Let's say, for example, if I want to do a selection on how my vertex is displaced, I need information on the track. And to build a correct track, I need information from all the different subdetectors. So that's where we're getting at. And okay, so why do we remove the hardware trigger? So a lot of people already told you this. So first of all, if you look at this graph here, if you see the evolution of the trigger yield, which is normalized to a certain value, its evolution throughout when we increase the luminosity. You see that in condition of run 1 and run 2, we hit it starts to flatline. And if we project this to a further luminosity, so in run 3, now we are at 5 times what we had in run 1 and run 2, we end up here with still a flatlining. So this is clearly not efficient. And we identified this flatlining due to the harsh cut that was done at the L0 trigger, where the output rate was limited to 1 megahertz. Another effect that was seen, so this is where this was done for some interesting signatures BDKs, and similarly here for BDKs and charm decays. If here we look at what efficiency we can expect for a certain rate of low level trigger, this is done on hardened properties that we got from the calorimeters. And as you can see, if you try to reduce the output rate of our LDO trigger, for example, to 1 megahertz, we see that the efficiency in selection drastically drops. So it's clearly not a viable solution. So the solution was, okay, low-level triggers don't work for us, hardware triggers don't work for us. Let's just remove it and see what we can do with softwares. So this brought up a lot of challenges because, as I said before, the detector produces a huge amount of data that we can't process, that we can't all save. So how do we do to process all that data, and how do we move it first to computing servers and computing farms? So this is done by optical fibers. So this is our detector. Here is where the collision happens, and then from those subdetectors, everything is brought back up to the data center from the PM85 shaft. I can't remember if it's the one with the elevator or not, but never mind. It's the next one. Okay, so this is not the elevator. And we bring everything back up to the data center. So this is done by roughly 250 meters long optical fibers. Okay, so now we have all the data, we had the collision, we have all the data from the subdetectors, and we can actually start doing things with it. So here we start working on event builder servers. As you can see here, each of the servers has three slots, DAQ, so data acquisition slots, which are FPGAs that are meant to get the data from the subdetectors. So at this point, we got all the data on our EB servers, but the thing is, on an added event, we have each of the different detector receivers ends, so all of the different DPAs will get information from different parts of the subdetectors. But we don't actually, what we want to do this now is regroup all the information that is linked to one particular event. So all of the different DPAs actually communicate with each other. And there's a whole process where all the FPGAs send out the information linked to one event and from the different subdetectors. And then we're going to regroup all the information from one event in one of those servers. So this is what we call event building. So we get the data from the subdetectors, we regroup them per event type, and we send this back to one of the event builders. So now we have packages that describe what actually happens in our subdetectors per event. Okay, so now we built all the information per event. What can we do with it? So a logical step will be to send the packages back to another processing farm that will start to apply selection and reconstruction. But what was possible in the servers that we use is that we actually already have slots available for GPUs that will be used for the first level of triggers. So those event builder farm are corresponding to 170 servers, and as I said, we have per building server we have 3 FPGAs, so that's roughly 500 FPGAs all throughout the event building farm. Okay, so we send the information from the cavern to the data processing, to the data center. We regroup all the data we have from the subdetectors into banks of information that are linked to each event. And now we want to start processing, because here we didn't change the output flow, the number of information we have. So that's what is done at the HLT1 level by GPUs. We're going to start to partially reconstruct the tracks to apply selection on reconstructed quantities. So the goal of HLT1, as you see, we are at a 30 megahertz rate. So the HLT1 has to be fast in decision making to select what we want to keep or not, because the data is going to keep coming. So it has to do a fast and partial reconstructed. Partial in the sense that we're not going to use all the information accessible from our full detector. We're only use certain types of information to do a fast reconstruction. So it's not going to be a perfect reconstruction, but it's a reconstruction that is good enough for us to start doing selections. So this runs on the moment on 1 GPUs per EB servers, but we actually still have 2 other slots available if we want at some point in the whole run to increase the computing powers. And I seem to remember that the second one is in discussion or already decided to be implemented soonish enough, but to be checked. So why do we use GPUs? So I am absolutely no expert in CPUs and GPUs, but roughly what I understood is GPUs, you have many little cores, so you're able to quickly parallelize different type of algorithm. But the algorithms that are treated by GPUs have to be simple. So it's more or less simple complications. That's why it has to be fast and partial. Whereas the more complex computations that will run on less cores, but cores that have more powers will be done at a second level on CPUs. But we'll get back to that later on. And also at this point, we have little knowledge of the magnetic fields as a detector. But yeah, all of this implementation is done on the Allen project. And yeah, I should have been a link here, but no, I'll add it afterwards. So I added a link to all the GitHub repository where you have all the scripts that is used and all the different selection. Okay, so now we have all the information per event. What do we do with it? So this is more or less how the reconstruction sequence is done at the GPU level, at the LHLT1 level. So what does the GPUs actually do? So I'm going to go through quickly through the different steps. So you have the raw data, you apply a general level cut, event cut, which is, from what I've been told, just a cut to select, to remove events that are too busy, with too many information that will slow the whole selection process down. So let's say we have 1,000 events saved that are going to be used, treated on a GPU. We're going to remove the 100 that are the busiest to not slow the whole process down. Afterwards, we're going to use different information from the different detectors in the same flow that the particle actually go through a detector. So starting information from the velo, then moving to the UT, the sci-fi, and so on. So at each step, you have decoding, muon decoding, UT decoding, sci-fi decoding, and velo decoding. Decoding is because from the subdetector, I'm going to have, okay, this pixel lighted up, but we have to translate this to do tracking into positioning in our three-dimensional space. So this is mostly what you can understand from decoding. Okay, so let's start by what is done in the velo. So as I said, we want to do partial reconstruction. So here it's this first point that we're going to start actually making some tracks. So since there's no magnet in the velo, we're going to start. We assume that the lines are straight, which makes sense. So we're going to just try and connect the dots in a straight line. So this is done by a search by triplet algorithm. So we're going to, at each of the models of the velo, we're going to select the hits that happen, and we're going to look at the neighborhood, the two neighboring modules to find 3 points that actually make a straight line. So we're going to regroup all the different we're going to select all the different triplets of points that make a straight line. And for each of those triplets, we're going to continue and go further on and further on in the different layers until we have matched all the points that could be matched in a straight line. So at this point, we have tracks in the velo from our model. And as you can see here, it works pretty well. So this is on simulations. It used 5 times of different types of decays, which cover mostly all the physics that we can expect in LHCb. So this is efficiency of track reconstruction at the velo state, so here, across the transverse momentum. And as you can see, throughout the whole PT spectrum, we do actually have an efficiency that is very close to 1. We are at the order of 99% of track reconstruction, which is very good. So now that we have tracks, we can start looking to find primary vertices. And to do such, we extrapolate the straight lines to the beam line. So and then at a point where both of them cross, we're gonna identify primary vertices. And to do so, we do that for all the tracks, and we make a histogram. Which amount of track has ended up at the same point, and that's what you see here. So for example, here you see that a lot of tracks come from this point. So forget the normalization, it's a weird normalization, but that's more or less what you need to understand here. And Z, of course, is the beamline direction in the velo. So from this, we have histograms of where the track met the beamline, we fit, and we get the positions of the different primary vertices. So we have tracks, we found where they came from. Oh, and then also here, this is can be pretty straightforward, but this shows the efficiency of primary vertices identification depending on the number of tracks you have coming to the primary vertices. And as you can see, the more tracks you have coming to the same point, the better you are in finding that point. But yeah, moving on. So okay, we did the first go of the information we had at the velo, and we're going to use this to study what happens now in the UT. So the UT is used to reconstruct charged particles that are either decayed after the velo or charged charged tracks of low momentum. So charged tracks that are going to be bent by the magnet afterward, and that will end up outside of the LHCb acceptance of the other, that won't see the next layers in our detector. So to start, so we use information on the velo. So we're going to use our track and we're going to continue extrapolating them towards in straight line towards the UT. But we can't do exactly straight lines because the UT is close to the magnet. So we're going to start to see a little bending, which is took into consideration when reconstructing tracks within the UT. Okay, but that's not a problem actually, because having a magnet field and having curvature gives us information on the momentum of that particle. So at this stage, we are already able to rebuild the first part of the tracks of the particle and also give information, a first estimate on what momentum has that particle and what charge, of course, depending on the sense of the curvature. So, and okay, so that's more technically, but we require that we have at least 3 hits in the whole UT to reconstruct the track. Same kind of plots across the PT range. Also, we see that we have an efficiency that is pretty good, but we start to see a bit of dropout at lower values of PT. So now, continuing forward in our detector, we end up at the Sci5 after passing through the magnet. So here, the tracks have been curved. They passed through the magnet and they deviated from what we already had, clearly deviated from what we already had at the velo. So since we have a first information on how they started to bend in the UT, we're going to use that information to not look for tracks in the whole Sci5. We're going to identify a region in the Sci5 in which we're going to start rebuilding tracks to save computing time, of course. So this is done by extrapolating what we have on the B field, information we have on B field to parameterize the trajectory. And yeah, as I said, you extrapolate the hit only in a certain region of the Sci5. So this works for tracks that have a momentum higher than 3 GeV, because as I said, the lower momentum will get lost after the magnet. And at this stage, even though it's only at 31, when I said fast and partial reconstruction, we are still able to have a momentum resolution of 1%, which is what the precision we want in LHCb. And as you can see here, it works well. We still have a nice flatlining towards 1 across the whole PT for higher values and a drop after a certain amount. Okay, and this, side note, in the Sci5, it's also done by triplets, finding triplets and then trying to make the different triplets and the different layer communicate with each other. Okay, so even though we still don't have a UT, we're still managing to reconstruct track pretty efficiently. So the only thing that changes between the UT, the algorithm with and without the UT, is that we don't have the initial information on how the track started to bend. So we don't have the initial charge estimate or transverse momentum estimate. So we can't say, okay, we are the Sci5, where do I look at? I can't say, I isolate a region in the Sci5 in which we need to look for tracks. So instead, what is done is we extrapolate what we had from the velo, because this is the only thing we have now, in a straight line. And from that line, we look on the left and on the right to see whether whether we see matching tracks that are linked to a positive charge or a negative charge particle. This works well for higher momentum constraints that I put here. And as you can see here, okay, after the low momentum cutoff, when we compare the efficiencies with and without UT, they are comparable at higher momentum. Okay, so now why do we have a UT since everything works well at as you can see here? So first, okay, this works for high momentum, and we are also interested in low momentum tracks, but also there's an increase in the go straight reconstruction. So go straight is when we reconstruct tracks that are not actually there. So false identification of tracks, which are clearly reduced when we take into account the UT. So this is one of the methods that is used that was commissioned in what we're doing now in our detector. There's another method I heard of, seeding and matching, when you use the sci-fi information independently from the information, and you try to see where both of the tracks, so what tracks we reconstruct in the sci-fi, what tracks we reconstruct in the fellow, and you start to see where they meet to see if they can form a whole track together. Well, okay, I won't go into details, but at the moment, two methods of tracking without UT has been commissioned in our detector. Okay, so now we have a track that has passed through all our tracking systems, but we need to improve, since at the big we have more information than when we started looking at the track in the velo. So we can improve our understanding of what was happening in the velo using what we did using the UT and the sci-fi. So we do what is called a Fit-Kalman filter, where at this stage we use all the information we have after the sci-fi to rebuild the track, to refit the track at the velo. So this uses the momentum estimate that we didn't have at the first place in the velo to take into account material interactions. So since we have a momentum estimate, we are able to characterize how the particle will interact in our detector. So taking into account possible multiple scattering or energy loss when it goes through our detector. So is this we try to improve our track, and this is at this stage for HLT1 sequencing only done at the velo level, whereas in later on stages of computing, this is done throughout most of the detector. Okay. So there's also at HLT1 levels, there's also some identification where you try to match the track that you find after the forward tracks, so after the sci-fi, into modules that have hits in the muon chambers to try to see whether that decay is a muon or not. So we do have some muon identification at the HLT1 level. And here, so I know very little about this, but I think it's interesting to have heard at least once. So this is actually new at the HLT1 level, and it's still ongoing, I think. We do have some calorimeter reconstruction. So we start at the HLT1 level, we do start to look at energy clusters that can be found in our different ecal. And this is used to, at HLT1 level, have photon and electron reconstruction. So to start enabling selections on electron and photons. And I know that some lines are already implemented at the HLT1 level, like in the software. And this is done for the first time. And if I remember correctly, this was not actually planned to be done when planning the upgrade. But thanks to a lot of hard work, it is possible now. Okay. So all of this reconstructions to be able just to do some selection. So and here are the different list of all the selections that are applied after we have done our reconstruction. So after the reconstruction, we have enough information to start selecting our data. And this is actually from the monitoring of a run that happened like a few weeks or months ago on our actual run. And here you can see the different the importance of the different selection lines at the HLT1 level. So you have some inclusive hardon lines, some calibration, muon, charm, monitoring, electron and photon, and here you have the detail of how this spreads out into the different implemented line. Yes, important point. We started up with the 30 megahertz input rate in our HLT1 level, and this is the total rate we have as output from our HLT1 level. So as you can see here, we are at the level of 1 megahertz. So this confirms that HLT1 does what it was planned to do and it works well, because in running condition, we managed to successfully reduce the input rate of 30 megahertz to 1 megahertz of output. So this is what we do here. So from the detector, we group the events of the subdetectors. We do first reconstruction to apply first simple selections. Everything is done very fast, and then we reduce the rate of the data flow. Next step, the buffer. So it serves to, it's a bit of a break in the whole data process. This is how I see it. So it's here for two reasons. First is on a whole events, that are passed by the HLC1, while some calibration is performed. I'll get back to it a bit later on. And also it allows for processing once the field is in between different LHC fields. So fields are not ongoing 24/7. So if we want to still be able to use the processing power we have, we can store the data in the buffer and then reuse it a bit later on to make the most of our processing farms. And I've found that in the recent upgrade document, where for a simulation of how the scheme of the LHCb fills, for an optimal buffer size, we'll have 30 petabyte of storage, and this could account for 80 hours of LHCb collision at a 30 megahertz rate and at an output rate of the HLC1 at a 1 megahertz. Okay, so the buffer, moving up, as I said, the buffer is used, the information stored in the buffer is used for real-time alignment and calibration. So what is it? So it's used, since we want to have a very good, in the next few stages of the selection, we want to have a better reconstruction. And to do so, we need to make the most of the information we have now. And the more we have understanding in our detector, the more we're going to have, we're going to improve the measurement of the selection we can do further down in our data stream. So this uses the first reconstructed information we have from HLC1 to recalculate the alignment and calibration constances. So this gives us in real time, so this is done while taking data and while everything is processed by the different selections. This is about information on how our detector is. And this was already implemented in Run2, and there's some changes to the techniques because our detector evolved, of course, for Run3, but I won't be able to go into much more detail. But as you can see, so this is on using Run2 data, but this is the mass peak before alignment, and this is the mass peak after alignment. So you clearly see the improvement in the resolution of the mass after using alignment as input in reconstruction. Okay, so the alignment is used for tracking system and rich mirrors, and so tracking system is all the different subdetectors I explained before, and then the calibration is for rich and the calorimeters. Okay. So now we have the data, we have done a first go at selection and reconstruction. We stored it, we buffered it. We did some real-time alignment, so we have the actual state of our detector. And then we're going to go at another go of selection and reconstruction with all of those information I had. So this time, so I won't go into too much detail because John will tell you more about how this is done in Run3. So yeah, so this is just a brief overview. So this time we do a full reconstruction. So, and we, at this point, we are able to reach the reconstruction quality that we would have done if we did the reconstruction offline, if we store all the data and then did the reconstruction at a second stage. So this is done because, as I said, we have the information on how our detector is. We have an island calibrated detector. See what I said just before. This time we also use the full particle identification we have at hand. So we use information from the rich and from the different ecal and hashcal if relevant. And we do a full tracking fit with detailed information on the detector and the magnetic field. So what I mean here is we do more complex Kalman fit that I presented before. So this runs on, if you go back to the HLC1, you see there's a few amount of lines, selection lines whereas in HLC2, the selection line, the number of selection lines is much higher. We account for roughly 1,000 selection lines at this level. So this was not the case for Run2, where we had roughly 100 lines, but a lot of the reprocessing was done at the stripping stage, was done offline. And the baseline in Run3 is set to all the selection that was done at the stripping level in Run2 is now moved on at the HLC2 level. So we move everything that was done offline to the online, since we can reach, as I said, offline quality reconstruction with all the new tools we have. So those selections are fine-tuned to specific types of signal topology or specific types of physics analysis. So this is up to the analysis to write his or her own HLC2 line. And this is what I've been doing at some point in my PhD, because if I'm going to do a measurement and I want to study a particular decay, I'm going to have to make sure that I have an HLC2 line that is fine-tuned to select the data that I will need to be using for my analysis. And as I said, this runs on CPUs. So CPUs less core, so a bit less parallelizable than GPUs, but more computing power. So cores that are able to do much more complex calculation, and so on. And all of this is implemented in more, and Jonathan will tell you more about this later on. So this is as another stage, we also reduce the amount of data that is flowing through our detector because we select on more precise and more complex selections. What do we do with the data once we have selected it? So now we're moving on more to the offline stream, which is, as I said before, handled by the DPA, so data processing and analysis. So from the HLC2 selection, there's 3 ways, and I'm just going to focus on this block and this block here. So starting by the data that is reprocessed at some point offline in the proofing stage. So the proofing stage is an offline selection that is used for data for physics data that are too big to be directly stored to disk. So for example, selections that are pretty inclusive or that have a high rate, a low rate, but a high event size. And yeah, I like to do the ratio to define a big event that can't be directly stored to disk. So generally, this, as I said, includes inclusive HLC2 lines. So in HLC2 lines, I would select a lot of type of data. For example, you have lines that will select 3-body decays. 3-body decays, there's a lot of 3-body decays that happen in LHCb. So a lot of data passes through that line. And at the spoofing level, we're going to fine-tune the selection to, for example, be to Kirchhoff 8H. So the 3-body decay selected that event, and then I reselect specific decay in that increasing line. And this is what is done by the proofing, and then it's sent out to the disk. So at this stage, we do not use any more reconstruction. We don't need to do offline reconstruction because we already did online at an offline quality. So the reconstruction that is used here is the one that directly comes from what was done at the HLC2 level. Moving on. So the next to those that pass through the spoofing, there's the turbo, as presented by Prima before. Turbo is where we already have events that are selected tuned enough to be directly passed from tape to disk without having needed to be reprocessed offline. So beforehand in Run2, 70% of the events were passed to offline processing, meaning most of the events were repassing stripping lines, as I mentioned before, whereas only 30% were passed to turbo. In Run3, we do the opposite. Like if you look at the numbers, almost exactly the opposite. Most of the event will be passed through turbo, which is the baseline in Run3, since we already have offline quality online reconstruction, whereas only 32 event will pass through another offline processing. So yeah, the turbo will bypass the processing step, so this allows to gain time in storage and computing power. And we save only the signal candidates and we remove all the raw data. So yeah, we reprocessed everything. Now we have data amount that is selected to what we want to do and small enough that we can write it to disk. And at this point, everything on this is going to be accessible in the bookkeeping that was presented yesterday. What do we do with that information? 2 things. First, we want to make the data user-friendly, and we pass through an N-tuple making, on which you will have a lesson. Oh, here you have the links. N-tuple making, which we will have a lesson by John later on. So this is based on the DaVinci software, so the same software as in Run1 and Run2, but there's a few things that changes. I won't go into the detail, but here are the major points. So we move from low-key to Thor functors, and we move from tuples to fun tuples. So tuple tools, as you remember, are where we regroup, we do families of variables that are useful to save to disk. So in those families of variables, there's a high chance that some are going to be unused, and this is why we move to fun tuples. Where in fun tuples you have to, so there's still some family, for example, for kinematics variables, but because they're used by everyone. But if you want more precise variables, it's up to the analyst to choose for, in a decay, for example, which particle will have which variable. So if I only want to store this type of information for that particular particle, I can now using fun tuple. So more flexibility on the choice of variable. This reduces the number of unused variables that just take storage space for nothing. And since the goal of all the data flow process is to reduce the storage and the computing use, this makes sense in our Run3 global philosophy. And also a quick word analysis production, but I think you already had a listen on this. So we move from user running their own jobs to a more centralized vision of things where you send up production to a whole global scheme. And this enables for automatic testing, automatic preservation of all of the configuration details, automatic errors, interpretation and detection, and finally you have a friendly web interface. And yeah, thanks for listening.
Okay, let's open the floor for questions. I didn't see any on Zoom yet, but again, if anyone wants to speak up and ask, you can do. But in the meantime, we can go to the room. Any questions? Yes.
Hi, thanks for the talk. So I'm wondering, could you go back to the slides with the ghost read?
Yes. I'll do my best to answer, but here you go.
Yes, so I'm just wondering that could you explain a bit more in detail, like how is the ghost read defined, and do you have any like intuitive explanation for the reason why without UT the ghost rate is much higher?
I can give you a guess, let's say. So first of all, a ghost rate is when, since we are in tracking, we are literally connecting dots. It can happen that at some point dots are aligned together, which are not coming from the same track. So we will be able to track that is not actually a track. So this is what we define as a ghost. And we do expect a certain level of ghost reconstruction, even with a UT, ghost connecting points. But without the UT, since we are, what I would guess is, since we don't have the information on where to look for a track, so we don't have the information on the first curvature that we can expect just a bit before the magnet, we have to look in both sides. And I wouldn't be surprised that even though a charge is positive, you will end up with a track here, the negative part, that also matches that. If I draw a line like this, that also matches what we could expect. And I would guess that this is because since we're just connecting dots and we don't have, we don't look anymore in a certain region of the sci-fi, we look at more globally the sci-fi, it's more probable that you're gonna miss it. Yeah, you have more points to connect. If you have more points to connect, you have more lines that are potentially matching, if that makes sense. And this is done, okay, so the ghost rate here is evaluated using simulation. So we have simulations, we know what the actual tracks are, we rerun everything, we will build our own tracks using this whole scheme, and then we compare the level of tracks we have. And yeah, that's more or less it.
Any other questions?
Hello, can you hear me?
Yes.
Yes, we can.
Yes, I may ask naive questions, but for the last for all the events, we will save all the good particles to our disk, or may we just save the decay process we interested in, such as the gypside decay, or the lambda C decay, or the D-meson decays?
I'm sorry, can you repeat your question?
Yes. Which decay process we will receive in our disk?
Okay. So this is depending on what you actually want to study. So you write HLC2 lines. As I said, they're physics dependent. So here, you write HLC2 line for the decay you want to study. So if I want to study a particular decay, the events that come from that decay will be selected by HLC2 line and then will be moved on to disk.
Yes.
You have to choose that. Yeah.
Okay, thank you.
So any type of decay that can happen in LHCb can potentially be saved if we select it, and that's a whole other. How do you select the decays? That's another topic. But, yeah.
Okay, it's clear. Thank you.
No worries. Thanks.
Hi. Yeah, thanks for the talk. This was a great summary. I have some questions about the sprucing. So this is run offline.
Yeah.
Okay, and yeah. So what is the? How do you make the decision? Either you use a turbo line or you should use some sprucing.
So this will depend on the amount of data that goes. Okay, so you see you have different percentage. That means that, let's say, how I see it, maybe I'm off. If anyone in the Zoom has more information or in the room, please do shout if I say wrong things. But let's say that 60% of the decision that pass the HLT2 level have event size and rate that are small enough to directly go to disk. Small enough saying that it'll be quick to write and doesn't take too much. Quick to process and doesn't take too much space. So that accounts for 60%, 68% of the data, of the things that pass through. 32% of it have either too high rates or and two events that are too big to directly be saved to this. That would take either too much time to process or just we have too much information. We need a second go at selection. So this is mostly the case for inclusive line. As I said, it's lines that will select a general type of topology of a decay that could within it have different. In which we can afterwards apply another selection to more refine. And I have an example of a friend of mine that had to do this for a decay that wasn't actually already planned at the HLT2 level. So it has some use for if I save all the 3-body decays, let's say, and that I didn't write HLT2 selective line, exclusive line that would select a tape. I didn't account for one of the decay. I can still go back to tape, apply offline processing to still reconstruct the decay that I haven't planned. If you kind of see the idea.
Yeah. So the output of these inclusive lines is also saved.
Yeah. So this it's saved but not as easily accessible. So what's on this is going to be in the bookkeeping. That's more or less the idea. And on tape, to go back, you can always go back to tape, but this it's a magnetic tape, so I have to read it out again. I won't tell you how, but you ask for some kind of tape to be reread, and so that you can reprocess the information. But yes.
So one will also be able to do this sprucing offline.
We can do, yeah, and this is what was done at Run3. We saved everything to tape, and then we reprocessed by stripping to then move it to tape. But yes, for this is especially like for high momentum or very rare decays that weren't expected to be seen in LHCb in our running conditions, you can always go back to what information you had before to then reselect those decays.
Yeah. Okay. Thank you very much.
No worries.
Hi, I'm also wondering, you mentioned that now it's possible to reconstruct photons and electrons at LH1 level.
Yeah.
Maybe I was wondering what opened the door to this reconstruction at that level.
What happens during this?
No, what opened the door? Like,
okay. I wouldn't know in details. I guess people just, as they're working on GLT1, started to look how this would be possible, testing it. And they saw that with our current architecture of processing, we are able to start looking at clusters. But the reason why we said, oh, let's do it, I wouldn't. Because I'm pretty sure that I've read somewhere that it wasn't initially planned in when we conceptualized not me, but we as a collaboration conceptualized the whole HLT1 sequencing. Yeah.
Okay, thank you.
I would say ambition of people, and that worked.
Any other questions? Yes.
Yeah, hello. I think I'm not able to read well the graph on the slide 15. So the efficiency in the velo, the last one.
Yes, sure.
Because if I see well, so higher is the number of track in the primary vertex, higher is the efficiency.
Yes.
Okay, but shouldn't be the opposite. I mean, if we have a lot of tracks, it's more difficult to reconstruct it properly.
It's the number of track that goes back to the same point. Like, for example, if I have only two, if I have only two tracks crossing at some point, how do I know that it's actually going to be a primary vertices? And how confident am I in saying this is a primary vertices? Where I have 20 tracks that end up to the same point, I'm pretty sure that I've found at first it's easier to find. And also, I'm pretty confident that this is actually a primary vertex. And this is what you see here now. So the number of tracks that go back to the same point, and obviously, if you have more tracks to the same point, you're more confident in this is a primary vertex. Yeah.
Yeah, makes sense.
Yeah, no worries.
Any other questions? No? I guess the only comment I can add to the question back earlier on the what you decide to store on tape and what you can do directly to turbo, again, it depends a bit of the physics. One quick example I can think of is then, again, very rare the case, containing electrons, for example, the reconstruction algorithm for the Bremsstrahlung emission takes a very long time. So I'm assuming that will be run offline in the sprucing and not on HLT2, but I may be wrong on this because it used to be run in the stripping. I'm not sure if that's moved into HLT2.
It actually started to be moved also to HLT1 level.
Oh, wow. Okay.
There's some
there you go.
From here. No, it's done at HLT2.
Okay.
I guess. But there's some tries in, like, this is what is underlying under electron reconstruction. There's some tests in Bremsstrahlung reconstruction at the HLT1 level where you like extrapolate the track that you had from an electron toward the cal. And if you see a matching energy point that isn't actually a track, you can start to reconstruct the energy of the deviated electron. But that's all I can say. But I know it's under investigation, let's say, or ongoing.
That is very cool.
And also, if you have any questions on like that raise afterwards on any topics I've brought up, please do come to me. There's a non-negligible chance that I don't have the answer, but there's a chance also that I know someone that does actually have the answer. So please feel free to contact me or reach out, let's say.
Thank you.
Sorry, just one more small question.
No, go ahead.
I know that it may not happen, it may not be the case, but if at some point you're not happy with your output of turbo, is it possible, is it available to go back and see the offline reconstruction and try to understand if you're more happy with that? I mean, is there any point of comparison? It's just a curiosity.
So I wouldn't have a yes or no answer, but I can think about it together, because the data taking is, as mentioned before, is always on the go to make sure that we're actually reconstructing what we want to reconstruct. So it's active testing. So if at some point we see that it's not processed correctly throughout, the correction needed or the improvement needed will be already dealt. But at the turbo level, everything that's processed by the turbo, No, actually, no, because you don't save the raw event as a turbo. You only save what passed the HLC2, what we have reconstructed at HLC2 level, reconstruction. But there's a non-zero chance that the specific decay you selected on an HLT2 line also passed through an inclusive line. So at some point, you can still, using the information you have on the inclusive line on tape, potentially reprocess the data and potentially compare. I know because the information on reconstruction is coming from HLC2. So but you still do save raw events at the tape stage, so you could potentially rerun the. I can ask.
I think the idea of turbo was just, again, to reduce the amount of space that you're using, right? So in that case, you are making the gamble of losing some information. But again, if you want to save more data, you have to make that choice at some point, right? So yeah, I guess Run2 has told us that the HLT2 level, they already managed in Run2 to achieve basically offline level of, for example, the PID. In HLT2, so on the online. So I guess we trust, let's use the we trust our outputs already at the moment, how the detector and how the reconstruction algorithm worked enough to say, okay, what we have reconstructed is good enough. We shouldn't, in most cases, again, there's a 28% maybe expectation, 26 of cases in which you may want to go back and check at raw data, but for most of it, we trust enough for your reconstructed, and that is enough for our physics analysis. And
there's everything has been tested in a lot of possible ways.
Yeah, exactly. So that's why we do commissioning and testing, and we save raw data in the meantime.
No, but it's a fair question, yeah. Yeah.
Oh, wait. I'll give you the mic.
It's still not quite clear to me. So at this 100K
Yes.
level, everything is saved or not? Like,
Alors, all the events that passed are saved. What we save from the events is not always the same. In a sense that at this stage, everything that passed will be saved. We save some information of it.
Okay.
And then it's the decision is what do we actually save from that event.
Okay.
So the triggering, this is the output of the trigger. This is a rate. We won't change this. This is for 100 events, that amount of pass through.
Okay.
What changes is what we actually store and because this is the whole point of turbo, where in the turbo we have the reconstruction information and also most of that what was used for the reconstruction. But since we already did the reconstruction and we are happy with how the reconstruction was done in the offline level, I don't need everything that's all the raw data bank. I only need what already passed the reconstructions.
Okay.
So I will only save this at the turbo level.
Okay. So what happens in this red box is that some information of this event is reduced.
Yes, exactly. Yeah, okay. This stage, exactly. You put it perfectly. It's data reduction. We're going to reduce what we actually save.
Okay, and the difference between the turbo and the other two is that in the turbo you cannot like reduce the part of the data.
We don't, because it's already implied in the turbo. You don't need to reduce it. It's already compatible with direct storage to disk. At the server stage, we save it as tape and we only save to disk what we want. Whereas here, the information that passes through is too consequent to be directly stored to disk. It needs to pass another selection to reduce the data, which here it's not needed. It passes through. It actually passes through proofing, but without selection. It's just, does that answer more or less your?
Well, actually, my only question is that suppose someone make a mistake somewhere in there, can we rerun it?
That's what we.
Can we rerun turbo? You mean?
Yes.
No.
No, but the sprucing we can rerun.
We can. Oh yeah, the sprucing we can, but it's not done for everything.
Okay.
Because yes, sprucing is done at a second offline level, so we have access to what is done on tape. But turbo is turbo, yeah.
Yeah, exactly. So again, the point of turbo is that to save space, you save less of the event. In which case, for non-turbo and calibration parts of the data flow, you save the extra bits of the event, the raw part, and you can rerun sprucing on that as many times as you wish. It's very computationally intensive, so it's not going to happen that many times. Just as the restripping campaigns that we have after run 2 were not that many, right? Because it's a computationally intensive thing to rerun everything back on the raw data as well. But turbo, you will not be able to do that. Once it's been reconstructed in that way, that's how it's saved.
And this is done during the data taking and the sprucing.
Yeah.
And there's some campaigns that between fills where there's like, that's what here, often end of year re-sprucing, but yeah, mostly this is done in real time.
Okay, it seems that unless there's any last minute question, which we have plenty of time for, it seems that today we're perfectly on time, which is unheard of. So it's 12 now, basically. We are planning for a slightly longer lunch break today. It's going to be an hour and a half. So we should reconvene at 1:30 with the first part of the hands-on session with more. So yes, we'll reconvene at 1:30 and have everyone have a good lunch.